So, welcome everybody. Welcome to my talk about food safety laboratories of the future. My name is Arjen Gerssen. I work at Wageningen Food Safety Research, which is part of Wageningen University and Research. I'm an analytical chemist by training, and currently I'm the program manager for food contaminants in food and feed. Today I will talk about the future of laboratories and especially the use of drones, smartphones, mobile equipment such as mass spectrometry. So if you imagine, if we look to the future of our laboratories, I think that things will change. So in the current situation, samples are sent to the lab to be analyzed, and then we send sample results back to industry. But we see a movement, and that's that more on-site and at-site measurements are occurring. And we foresee that farmers, for example, or transport or during storage, that farmers or inspectors are checking with mobile equipment the quality of the food or the feed and send the results to the cloud and then get a result back if it's okay, if it's not okay, or if it's suspected. And that can be done at different stages. So during production, transport and storage, but also in retail, where storage owners can check the quality of the products that they bought and also the quality that they sell. And then at the end, when you receive the samples or you have the food in your house, and you want to check the quality, for example, allergen detection, you can do that at home and you get a result immediately via an app or via a smartwatch. And of course, this will influence the whole situation, how we look at food and feed quality at this moment. So we at WFSR, Wageningen Food Safety Research, think this will change. And I will talk today about use of drones, smartphones, cameras for spectral analysis, and mobile equipment that can be brought on location. Also, the technician of the future will change. It will be more data-driven, so we will more check on the quality of all the data that's collected, and there will be loads of extra data coming in. So it will be more a data manager and a data technician, and only the samples that are suspected, so that they are not clearly okay or not okay, they will be sent to the lab for further analysis to see what's wrong or what's potentially wrong with the system. And this is still a very simplified picture of what I'm going to talk today about, because you can imagine that during all stages, waste will be produced, and then with the circular economy, so if a test is failing, it's giving a red sign, it will be treated as waste, and we should prevent that it will come up into our food chain again. So this will be a big challenge for the future. And I will talk today about what the WFSR is doing about this. So the current strategy, samples are taken on site, for example at a farm, then they are written down, they are transported to a laboratory. In a laboratory they perform a screening analysis, and only a small percentage is suspect. Then from the suspects a confirmatory analysis is applied, and then subsequently only a small amount is non-compliant. And you can imagine that all these steps are quite laborious, costly for industry, costly for laboratories, and also lab technicians are most of the time looking at zeros. That is of course a waste of money and of time. So what we expect is that we will get a paradigm shift where on-site more samples will be pre-screened, and instead of sending all the samples to a laboratory, only the suspect samples will be sent to a laboratory. So that's only a few, and then they will be written down, the administration transported and confirmed in the lab, and then we have a higher percentage of non-compliance. But we test only the interesting samples in the lab. So that will mean that the sample volume is changing to more interesting samples, but it will allow the industry and producers to have more samples screened at site before sending them to a lab. So this will be a big change for how laboratories currently are working. So as I explained in one of the first slides, is that I will talk today about the tools for food safety and quality control that are under development, and where I think that in the future will make an important role in testing for food quality and safety. So what's the role of our institute? So we're not machine builders, make that clear. So we don't develop our own smartphones, we don't build our own cameras or mass spectrometers. That's something that vendors and tech companies should do. However, we do collaborate with these machine builders. So for example, we collaborate with vendors building mass spectrometers. So we give them the constraints for mobile mass spectrometry, for example. Should the mass spectrometer have a certain weight, certain power consumption, etc. And if they develop these things, we will test them in the alpha and the beta phase. But also existing technologies that are available already, for example, drones, they're already on the market, but we try to hyphenate with existing technologies, existing detection techniques that maybe were not foreseen to be used in food safety control, but we hyphenate them with existing technologies and make a new product out of it. And then we apply them in our research field. So we develop applications, we validate them, and then we try to bring them to the applicants. So that are, in our case, food inspectors, but also sometimes for consumers where they can use fast and rapid testing. So I will focus on the topics I mentioned. So I will talk a little bit about drones. With the drones, they're already on the market for quite some years, but you still see a lot of developments in there. So, for example, they're now used in the Wageningen University as a drone team, and they are also focusing on precision farming. So where in the field does the crop need a certain amount of fertilizer, etc. And these drones are not the small drones that maybe you know from your children that are taking photos, or you take photos yourself with the drone. These are big drones that can carry quite a large weight already. So you can imagine that future equipment that is small can be mounted underneath these drones. They can be made for delivering goods, that's already known and under development, and also important, for example, with the AED machinery, that it can be rapidly applied on site. But we use it mainly in this presentation for remote sensing. So remote sensing, I give two examples what we do with it. So MDMA from ecstasy ended up in maize. And that is, of course, a potential problem for food safety when we eat it, or even if it's going to animal feed, then it can be an issue. And the other is with big fire incidents. Measurements on site is a risky task. So in our case of environmental accidents, which WFSR is also involved in, we can measure in the cloud with a drone which type of substances are present. So for example, we have these metal oxide sensors, and these are quite interesting. These sensors are also used nowadays for the breath testing for the coronavirus. So it's the same type of technique. What we do, we combine a chemical fingerprint of a certain product. So in this case, it's manure. And in the manure, we measure a certain profile. But then we also measured manure with drug waste, and you can clearly see that the profile is different. So if we load all these profiles into a chemometric model, we can learn actually when we are flying with the drone, is it manure what we smell with the drone, or is it drug waste what we smell with the drone? So this is an interesting application that's under development, and we're involved together with the NFI and with the police sometimes with testing these type of applications in real life already. And you can imagine you can fly over a field or fly in an area, and you can cover a larger range of area instead of moving yourself around certain fields. So that's a benefit of using a drone. So what I say about the fires. So we made some fires on our own parking lot and the parking lot of fire brigade area. And we made several fires and we measured the smoke, and we built actually a classification model. And you can see, for example, that if you have auto car and rubber from the tires, that we can classify it 100% correctly. And you can see that we can classify all these type of smokes that are produced towards their product. And they're almost all correctly classified, with the only exception with salad oil and cooking oil, which most likely is comparable in composition. So there the classification was slightly wrong. So this can be helpful because in some cases, in some type of fires, PAHs, PCBs and dioxin can be formed. And these are a potential problem for animals that are outside and also for food safety. So this is an important thing where we can already predict, okay, will this be a food safety incident, yes or no? And the other thing is that we want to develop is, instead of sending a person into the field to cut some grass, is that we want to have the drone equipped with a remote sampling device so it can cut grass, bring it back to the fan, and the fan will drive to the lab for performing the sophisticated dioxin analysis, for example. So that were the drones. Then we move on to the smartphones. So imagine the smartphone, the mobile phone you had 15 years ago is completely different than the one that you have now. Now it's a small computer, or it's actually already a big computer. You do a lot of things with it. So you can imagine that in laboratories, this will also play an important role. So Wageningen Food Safety Research is involved in the Food Smartphone EU project. We're coordinating that project. And what we do is that we use the smartphone in combination with biochemical recognition elements, so antibodies, for example, to develop ultra-fast detection techniques. And we use the technique of the smartphone, such as the camera, but also the Wi-Fi and the processing capacity, to analyze samples. We combine it also with electrochemical detection via portable potentiostat. We use 3D printed microfluidics. And of course, everybody knows how to operate a smartphone, so it should be robust and easy to use. Of course, software is another important one. You want to have an app that is quite easily to be operated and that we can use then easily. So an example is that we developed in the project together with our collaborators in Sweden a microfluidic device, which is shown here on the right hand side. This is actually a small system where we can pump with finger pumps solvents like the sample, the blue one, and the substrate, the green one, together with the marker. And then we have a coil where we can have a reaction, and then we can have a color reaction, which we can read out with our smartphone. So with this, you don't need any pumps. You just press it with your finger. It's silicone tubing, and you can mix solvents and samples, etc. So you don't need to have any pipetting skills, and you can couple it to a 3D printed device, and you can quickly analyze certain compounds that are relevant for food and feed safety. So this is one of the developments that is ongoing, and then you can imagine that the type of phone and the position of the camera can be somewhat problematic because you have to print your own new 3D device for your new smartphone because your camera has been moved. So for allergen detection, we also have a PhD in our institute, Gina, She worked for 3 years on the development of lateral flow devices that we can incorporate with smartphones. So an example that I showed here is hazelnut allergens in cookies. Of course, if you're allergic, you want to make sure that the product you consume is not containing these allergens. So would it not be ideal that if we have our own lateral flow device, let's say a pregnancy test, where you can test the presence of such an allergen? And you can see here with different concentrations of allergens that we have a control line, the upper line, which is always present, and the bottom line, which is gone. As soon as there's no allergens, it's completely gone. If there's a lot of allergens on the left-hand side, the 100 ppm, you see quite a clear black line. And this assay is quite rapidly. Within 30 seconds, this test develops from an extract. But now you have to interpret it by eye, what the concentration is. And you can imagine, now we have all the concentrations present, so you can see that the 5 ppm is a little bit brighter than the 2.5 ppm, but still it's very difficult to distinguish between the 5 and the 2.5. So with help of the mobile phone, we can make a picture out of it, and you have quite a sensitive camera, and then we can construct the whole calibration curve and determine the amount of hazelnut peanut protein present in your sample. So it's more reliable than doing it by eye, because it's an objective observation by a camera using the RGB codes that you measure. So going from the small cameras in the phone, going to more sophisticated spectral techniques. So Phasma-Food is one of the projects where my colleague Yannick Beespoel is involved, and he developed together with tech companies this nice camera that you see over here. And the camera actually contains multiple sensors. So for example, it can measure visible light, it can measure UV, and it can measure near infrared. So it contains a wide variety of sensors in a single camera. So by using this technique, we were able to, for example, measure olive oils. And if we look to extra virgin olive oils, you can see we have a fluorescent signal. On the right-hand side, we have the visible light signal, and we have the near infrared signal. A lot of peaks or bumps are present. So by doing data fusion and building chemometric models, we were able to make a model for extra virgin olive oil. And where you can see on the left-hand side in the table that if you were using only one of the techniques, so for example, if you were using near and you have olive oils composed of refined olives, you will only classify correctly 37%. But if we combine all the three sensors, and that's the combination of the decision tree, you can see you have a very high probability that you can detect adulterated olive oils with 10, 25, and 50%, up to 91%. So you can see that the combination of using multiple sensors is giving a lot of strength for this online or at-site screening using this sophisticated sensor. But there are also more easy sensors. So for example, Xio produces a near-infrared sensor, and this is the size, so it's like a lighter. You can see the top right where actually a file with cocaine is standing on top of it. It's making connection to your mobile phone. And if you have a correct database, it can help you out with testing the quality of cocaine. So together, for example, with the Forensic Institute in the Netherlands, we worked on testing these scanners for cocaine. So we used 13 different scanners, and each collected 5 spectra. And in the top, you can see the raw data, where we have all the raw data present. Then we apply some tricks to the data. And then you can see that all the lines are actually falling coincide. So that means that they all produce the same quality of data. And the top is actually 86.6% cocaine. And at the bottom, the red lines are the cocaine again, but the green ones are actually adulterated cocaine. And you can clearly see that there is a differentiation between the red and the green lines there at the right bottom figure. So this will help to quickly see if they are caught with cocaine, if it's true cocaine or if it's contaminated cocaine. So this type of scanners can help quickly to measure on site, and you can use them for a whole variety of parameters that you can test, for example, sugars or fats that are present. So the last part that I want to highlight is the transportable lab equipment. And here we can see that there's a big change. So the previous techniques that I showed are actually developments for with smartphones for single compounds screening, so no confirmation on location. But then if you have a suspect result, it should still be for official control being confirmed at the laboratory. So still these tests should be done in the laboratories we currently have. And for the spectral cameras, they are looking to macro composition of compounds, so not at the ppb levels that we want to look at when we have a contamination. So bringing the lab equipment to the locations, that will be a big step forward, especially if we want to use for confirmatory analysis, and then we have to use mass spectrometry. But these have still some constraints. So they're still heavy, so the small transportable mass specs are up to 35 kilograms, which is still not that heavy, but if you have to carry that through the fields, that is still a problem. So you can use them in the back of your car, but walking around with it is more difficult. But there are already some true portable mass specs, so that are shown here on the right-hand side. So they should be light, and we should be easy to operate them, and to have no extra power consumption, etc. Also for the screening, the smartphone is only looking at a single target, but here we also have what we call a multiplex, so we can look at multiple compounds that we test at once. So an example of this is a Luminex platform, which we actually brought on site near shellfish industry, where we can look at the presence of multiple toxin classes in the shellfish. And these toxins are quite severe, so we should rapidly test them. And nowadays, still samples are being sent to the lab, rapidly analyzed within a day. But still, of course, you can imagine industry wants to have solutions faster than a day. So with these type of equipment, they can analyze multiple toxins at site. So same as with the lateral flow device, so the pregnancy test, but now with magnetic beads, which can have different colors, different type of reds, and we can couple different type of antibody with toxin to it. So this helps us to analyze up to 500 in theory, different type of compounds at once in a single measurement, while with the pregnancy test, you can only measure a single compound or maybe 2 compounds or 3 compounds. So this is a benefit, but still you need a small lab or a back of your car. So the transportable lab equipment will be the last part that I will discuss about. So in the current workflows, we have samples, we perform extraction, then we do chromatography, then we ionize, we generate a mass spectrum, and that's how the current workflow is. What we see for on-site analysis is that samples are actually directly or quickly shaken with some solvent and directly introduced into the mass spec. So no sophisticated extraction and chromatography anymore. So one of these examples, and that's just recently published by my colleague Josja, is that we coupled this to a transportable mass spec. So what you see here is, where number one is, a small blade, which is called a coated blade, and we coupled actually it to the mobile phone. And we generate from the mobile phone 2,500 volt to generate the ionization of the sample that's on top of this blade. And then we can analyze it in the field. So we don't need a big power supply for generating electrospray. We just can use our mobile phone to do this. So this development is actually patented, or the patent is pending. And there we see that we can use with a mobile device coupled to a mass spectrometer these type of developments. So truly portable, that's where we want to end. So no external gas or power supplies, and we have one of these systems. And what I already mentioned in the beginning is that we want to have equipment from other areas. So this is actually more from the military area, where they look to nerve gases, but we brought it to food safety analysis. So it has a simplified readout for non-technicians, so they can measure, for example, if there's a drug waste, directly the composition that's present in there. And it's electro-impact spectra, so that will give actually already with a good library a match to compounds that are present. So for in this example, we see that toluene was detected. The system is from off to on within 10 minutes. So for conventional mass spec, it will take at least hours to have it up and running, but with this, it's within 10 minutes. So we use the same for checking for adulteration of peppers. So we have black peppers and, for example, papaya seeds, which you can differentiate by seeing if it floats in water, yes or no. But you can imagine that also mixtures are made from different type of peppers, and if it's a powder, it will be even more difficult to detect. And spices adulteration is quite commonly occurring, unfortunately, so that's an important area of research. So what you see in this picture is that the top picture is the true pepper, and at the bottom you see the adulterated pepper. And you see there are quite some similarities. For example, the aromatase that's present in both, but the limonene is only present in the real pepper, and it's actually absent in the adulterated pepper. So this gives a signal that there's something wrong with this adulterated pepper. So challenges. There's still many challenges for moving to the field with equipment. So for example, how will we assure the quality? If a technician is measuring in the lab, it's trained, it's having all the quality controls. But if somebody else is working in the field, you don't know which type of quality he's performing. So quality controls should be incorporated so that remotely we can test if the system was operated correctly and the measurements were done correctly. Also then, we need to accreditate these methods, and accreditation is now for a building, but to have it on site, it will be a challenge. And then if consumers start to use these tools, it will influence their behavior. If a certain product of a shop is positive for something or advised not to be eaten, then they will share it on social media. And if they did their test wrongly, then yeah, you can imagine that delivers some problems. So technical improvements, portable mass spectrometer still needs to be more sophisticated. So now for the GCMS, we have one, but for the LC, the electrospray, we only have single quads, and there we need to have triple quads for more selectivity and more sensitivity. And with food safety, we're looking at low concentration, so it's important to measure these. So our change on classical laboratories should change. So we assume that in the coming years, the classical laboratories with their regular instruments, the workload, the work volume will shrink, and the market volume will also shrink. But for the high end, so the suspect samples that need to be analyzed, they actually will increase. So there will be more high-end laboratories for this minor amount of suspect samples that still need to be analyzed. And also the personalized and the on-site development will be increasing. So this is my view on where we go with food safety analysis. So I would say be prepared for the future and think about how your lab should be equipped with the staff and with your technicians in the near future. So with that, I come to the end of my presentation. I want to acknowledge my colleagues, Sandra, Yannick, Marco, and Michel, and also all the funding agency that makes these projects available for us. So with this, I want to thank you all for listening, and I wish you a pleasant day. Thank you. Bye.